As you guys saw, Maya really wanted to come and teach. Her handwriting isn't so great, so I've asked her to wait until tomorrow for her teaching. Okay, so welcome everybody. Good morning. Hope you've had a wonderful morning, as I have. If you were listening in, I've already managed to play much in the snow. So we're going to start our fourth lesson today, and our outline is going to be, we're going to first finish up. We're going to continue talking, well, we just kind of started talking about dark sectors and models, and I hope to convey to you how easy, simple, generic it is to achieve many of the mechanisms that we've been speaking about in the context of actual models. And after we talk about dark sectors, we're then also going to just discuss towards the end sort of general constraints that you should kind of keep in mind when you're perhaps constructing your own mechanism or working on some model. Okay, so that's going to be our plan for today. So let's start with our dark sectors. So this is dark sectors, and I'll call this continued because we did start kind of talking about this together yesterday. And so as we saw and as we discussed, we're going to take inspiration from the standard model. And so we're going to be talking about strongly coupled gauge theories. Okay, so we're going to be talking about strongly coupled gauge theories. We've already seen a simple gauge theory, which would have been just an abelian U1, but we're going to be talking together now about what happens when we have these sort of strongly coupled gauge theories. These are QCD-like theories. And as we discussed very much at the end of yesterday's lesson, in these theories, because we have, it's so rich, it's really a very rich playground for many mechanisms to emerge. And in particular, these theories, if we think of something like QCD, then just like we have all of the mesons of QCD, we similarly can have a whole bunch of dark mesons that we're going to be interested in. And in particular, the pseudo-Nambu Goldstone bosons of these theories, so pseudo-Nambu Goldstone bosons of these theories, which I'm going to collectively call here the pions, or more accurately, the dark pions. Okay, these can play the role of dark matter. And so the first thing that I'd like us to do is just to sort of give you an example. Let's, for instance, just look at a whole bunch of the different 2-to-2 processes that we've discussed together. Okay, so just within this very generic setup of strongly coupled gauge theories, here's a whole bunch of processes that can, in principle, happen. Okay. Oh, there's a question, Giovanni? Is there? Okay, maybe it's an accidental question.
Giovanni, did you raise your hand? Okay.
Okay, so I'll continue, and if the question comes back, feel free to ask. Okay, so here are a whole bunch of processes that we can write down in such theories. Okay, so let's, for instance, look at the following. I could have pions. Okay, and now when I'm saying pion,
can you hear me now?
Yes.
Sorry, I think my mic wasn't working. No, so I was just wondering, why are we expecting the pions and not, say, the baryons, like for baryonic matter, to be the most consistent bulk of?
They could be. It could be that they're dark baryons. We're going to see that there's a lot of predictability associated with dark pion. And so I want to reiterate something that I said yesterday. What we're working through now, this is by no means to say these are the only dark sectors that one can write. This is the only dark matter. That's absolutely not the direction. What I want to show you is in a very broad class of theories, how just by saying, okay, maybe it's my pions that are the dark matter, and just to show you how just with that simple statement, which could happen generically in many of these theories, how so many different mechanisms of dark matter are going to emerge. Okay, so this is by no means to restrict to only this, but just to give you an example of how generic it is to be able to see these mechanisms. Okay, all right. Is that attitude kind of clear?
Yeah, thank you very much.
Okay, great. Okay, so here I could have, for instance, dark pions exchanging a dark pion and going into dark rows. Okay. So right now I'm not going to keep writing this sub-index D. So when I'm writing pi's and rows, these are all my dark particles. Okay. So in theories of this sort, typically, the mass of the rows, usually the pions are the lightest of the mesons. And so this would be in a regime where, for instance, we'd be having, forbidden process. Okay, so this would be a forbidden 2-to-2 annihilation that we could have. We could also have these dark pions. Here they are over here. They could be exchanging pions and going into our dark photon. Okay, so this would be just sort of ordinary 2-to-2 annihilation. So this would be sort of a WIMP-like process. We could also have, I could have, for instance, let's say I could have here pions going through an S channel of this kinetically mixed hidden photon and kinetically mixing into the ordinary photon and then going to standard model particles. Okay, so this would be also a contribution to 2-to-2 annihilation as part of a WIMP-like process. Let's think what else we could have. Okay, we could also have elastic scattering. So I could have pions that are elastically scattering off of standard model particles by exchanging this kinetically mixed hidden photon. So this type of process is an elastic scattering process. So this would be, the process that, for instance, if we were talking about SIMPs, this is a process that would give us kinetic equilibrium, or this could be a process that is actually responsible for elder dark matter. Another type of process that we can write down is something that we didn't work out in detail, but we did draw it the first time that we talked about 2-to-2 processes, and I gave you a reference for it. It's when two pions will go to just one pion and something else. So this is a semi-annihilation process. This is something that also can happen, and potentially many more. Okay, so in principle, just in terms of 2-to-2 processes, I've already shown you how this very generic set of theories can have many different processes that, depending on which one is dominant, maybe will lead us to different types of mechanisms for dark matter. And so what you would do in principle, okay, once you have this, you have your theory and you write down all of your types of contributing processes, contributing diagrams, what you'll do in each case is take, your particular Lagrangian, which is written in terms of the parameters of your theory, and you're going to go ahead and compute what is the cross-section that you'd need for the relic abundance. Okay, so in each case, what you do is you can compute from your Lagrangian. Okay, so your Lagrangian is now going to be written in terms of, you no longer have some effective alpha, all these different parametrizations that we did in our mechanism level. Now you have a Lagrangian. Your Lagrangian has its parameters. It has its dark fine structure constant. It has the mass of the pion. It has the K constant of the pion. It has the mass of your vector, etc., etc. All of the parameters of your theory, of your Lagrangian, and you can compute from that the cross-section that you need for the dark matter abundance. Okay, so what I mean by that is, let's say you wanted to work out, well, what if this forbidden process is the one that's contributing? So you'll go ahead and compute, okay, here's my sigma v for this process, and this is some function of your parameters. Okay, and then what you can do is translate this sigma v into translate the sigma v that we developed previously at the mechanism level, and now sort of translate that into what does this mean for the parameters of your theory. Okay, so what we do from this is we translate the cross-section we developed previously into this model. Okay, to see now what does this cross-section imply in the context, what if this is what's responsible for dark matter, what does this imply on the parameters of our Lagrangian? Okay, to understand what parameters are needed here. Okay, so this is sort of the general recipe. You take your particular theory and you look at all your processes. There's one particular one that you're interested in understanding what, if this is the one that's dominant, we already know at the mechanism level what we need for the cross-section. You write the cross-section in terms of, you compute it in terms of your actual Lagrangian parameters, and then you can do the translation between the two to understand what is literally implied in the context of your theory. And so you can do this for every single one of these types of processes. The one that we're gonna do now together in detail is instead of doing a 2-to-2, which is sort of a little bit, I think, easier in principle to do, we're gonna work through it together. For instance, 3-to-2 SIMPs, okay? So I'm choosing these because in a way, 3-to-2 processes in a way might seem like the most exotic from the types of processes that we've talked about. They're kind of less familiar than 2-to-2 processes. Okay, so 3-to-2 might seem, might seem more quote unquote exotic than 2-to-2 processes, which are more familiar. But I'm a little bit cautious when I say they might seem a little bit more exotic because we actually have 3-to-2 processes in the standard model itself, okay? We actually have 3-to-2 in the standard model. That was the weirdest 3 I've ever written. Okay, so how does this happen? So let me give you a brief reminder of what actually happens in QCD. Okay, not dark QCD, literally QCD. Okay. So here's what happens in QCD. Okay, so QCD is, of course, an SU3 gauge theory. So it's an SU3 gauge theory. And in principle, I have 3 light flavors. Okay, the up, the down, and the strange. And this theory has a global symmetry, which is not what we enforce on the theory, but what just happens when we write down this theory. We have an SU3 left cross SU3 right global symmetry. And then as we flow down to the IR, we can flow down to low energy, our theory confines and chiral symmetry breaking occurs. So the theory confines and chiral symmetry breaking occurs. And what chiral symmetry breaking does is it breaks this global SU3 cross SU3 down to the diagonal subgroup. So this SU3 left cross SU3 right breaks down into our diagonal subgroup. Okay. Now in QCD itself, these global symmetries are only approximate because the masses of these light flavors are not degenerate. Okay, so this is only an approximate symmetry. But this theory has, so if I have SU3 cross SU3 breaking to SU3 diagonal, I have 8 broken generators. And so this theory has 8 pseudo-Nambu-Goldstone bosons. Has 8 pseudo-Nambu-Goldstone bosons. And these are what we know as the kaons, the pions, and the eta. And this theory of QCD has 5-point interactions. So we have 5-point interactions. Because what we have in this theory are 2 kaons that annihilate into 3 pions. And this type of interaction happens in the QCD Lagrangian through a very particular term in the Lagrangian, which is a topological term, which is called the Wess-Zumino-Witten term. Okay, so this happens through a topological term in the Lagrangian that's called the Wess-Zumino-Witten term. Okay, and I'll give you the references here. So this is based on, there was a paper by Wess and Zumino in 1971, and then 2 beautiful papers by Witten in 1983. These are really 2 beautiful papers by Witten. I highly recommend reading them. So this term, what happens is that if you take this term, and we're going to write it out in a moment, but if you take this term in QCD and you compute the rate for these 3-to-2 annihilations, you'd find that it would be just right to be a SIMP. Okay, so it would give you just the right rate that you need for a SIMP if the mass of the involved particles is of order 100 MeV. Okay, so let me just write that. If you calculate the rate, you'd find that it's just right to be a SIMP if the masses are of order 100 MeV. Okay? And so inspired by this, let's look at what could happen in QCD-like theories. Let's look at these QCD-like theories. Okay. So here's what we're going to do, and let me just write it out explicitly, for instance, for an SU case. Okay, so we have an SUN gauge theory. Okay, so suppose we have an SUN gauge theory with some number NF flavors, okay, which have degenerate mass. Okay, and this degenerate mass is going to make all of our global symmetries be now exact. Okay, so unlike in the standard model itself, where the symmetries are only approximate, here we are actually going to have a residual symmetry that's going to be exact thanks to these degenerate masses. But I have an SUN gauge theory with NF flavors. So this theory has, before chiral symmetry breaking occurs, it has an SUN left cross SUN right global symmetry. And once chiral symmetry breaking occurs, what happens is that this breaks down to an SUN diagonal. Okay, and this SUN diagonal is an exact symmetry of the theory. Okay, thanks to these degenerate masses. And so depending on n, of course, there's some number of broken generators. And so there's some number, I'll call that generally n pi, of pseudo-Nambu-Goldstein bosons. And these is who I collectively call the pions. And these pions can play the role of dark matter. And so this theory has 5-point interactions through this Wess-Oumino-Witten term. And let me write it out for you now explicitly. So here's what this Lagrangian looks like. The Lagrangian for the Wess-Oumino-Witten term is, it has a very particular form. So it's 2n, n is the number of colors, divided by 15 pi squared, f pi squared, where this f pi over here, oops, this f pi is the pion decay constant. Okay, the pion decay constant of the theory. And then it has this, it's contracted in a particular way. So there's an epsilon tensor epsilon mu nu rho sigma. And then I have a trace of pi, oops, pi d mu pi d nu pi d rho pi d sigma pi. Okay, so you see it's a term that involves 5 pions contracted in a very particular way. Okay. So this is 5 pions contracted in a particular way. Okay. And so from this term, and maybe I'll just emphasize over here that this type of term looks identical. We've now done this for the SUN case, but you can do exactly the same thing. So we can do this for we can do this for the SUN case, but we can also do it, sorry, that looks like an O, we can do it for an SUN case. We could also do it for an SON case, and we can even do it for an SPN case. Okay, so for any of these gauge theories, provided we have enough flavors, so it's 3 or more for the SUN and SON, and 2 or more for the SP case. So provided we have enough flavors, which is a very minimal content, we have the 5-point interactions through the Lagrangian. And what this means is that these theories give us, in this very generic way, sorry, actually, let me draw this differently. Okay, because this is no longer a blob. This is, a particular Lagrangian term that gives us 5 pions interactions, and in particular 3 pions that can annihilate into 2 pions. Okay, so this simp-like 3-to-2 process is completely generic. Okay, so this is generic in QCD-like dark sectors. Okay. So let me show you what I mean by we take our Lagrangian, and now we have a process, and we want to compute we understood previously at the mechanism level what type of relationship between mass and effective coupling we needed for SIMP dark matter to be responsible for the relic abundance. Let's see what happens in this particular Lagrangian case. So I'll just write that out for you. So if you take this Lagrangian over here, this Wessel-Witten Lagrangian, then you can compute what is the size of this cross section. Okay, so here it is. So what you'll find when you do that is that this sigma v squared 3 to 2. Okay, so the thermally average cross section for this 3 to 2 process, you can compute it. This was very painful to do when we did this computation. Is 5 square root 5, 2 pi to the 5th, n squared, number of colors squared, over x freeze out squared, times m pi to the 5th over f pi, the decay constant to the 10th power, times something else that I'll call t squared over n pi cubed, where this last piece, and this is the only reason that it was somewhat painful originally to compute, this is some combinatorial factor that depends on the gauge group and on the number of flavors. Okay, so this is just a combinatorial factor that depends on group and NF. Okay, but it's just something that you can go ahead and compute. And what this means, now that I have this cross section, I can now take this cross section and I can now look at, instead of using some effective alpha and mass, I now have parameters of the theory, and I can look at what is the relationship between the mass and the couplings in this theory. And so I get something that has the following. So let's say I'm looking here at m pi in units of GeV, and over here, instead of some alpha effective, what I now have is the parameters of the theory, and the natural choice is, for instance, m pi over the decay constant. Okay, and so what one finds is that there's a curve over here of the solution to the Boltzmann equation such that you get the right relic abundance. Okay, and so it's roughly something like over here, this is 1 GeV, and here this is, let's say, of order 10 MeV. Okay, so this is the solution. Oops, this curve over here is the solution to the Boltzmann equation. Okay, so this now replaces that alpha effective that we used in the absence of a particular theory. Okay, and of course, in order for this theory sort of not to explode, there's some limit on how high can we take m pi over f pi, and so roughly this shouldn't be larger than around 2 pi. Depends a little on the normalization. Okay. But this shows you now how you get something that looks very similar for all of these different gauge groups and all of the different number of flavors. You're roughly pointed to this dark matter masses that are typically of order sort of more like the 100 MeV scale. Okay, that's sort of the ballpark to keep in mind for these dark pions. Okay, and let me just give you also the reference for where you can read about this more, where we first arrived at these dark sectors. These types of QCD-like theories give us SIMP dark matter. So there's a set of papers. So the first one in which we did this was a paper with Eric Kuflik and Hitoshi Murayama and Jay Wacker and Tomer Volansky. So this was a PRL of 1411.3727. This is the first paper, and the name of this paper is The Simplest Miracle. And then another paper in which you can read a little bit more is also a paper with Eric and Hitoshi Murayama, which is 1512.07917. And this is a paper that also includes exactly how to include a dark photon into the story. So this one includes dark photon. Okay. So what we've now arrived at is that these QCD-like theories, which are completely generic, there's absolutely nothing special about these theories, they naturally have SIMP dark matter in addition to all of these different 2-to-2 types of interactions that we could have. Now, I know I was asked earlier also about baryons. And of course, if the baryons are your lightest particle or your lightest states, then one can also think about ways to work with that as dark matter. I'm just going to give you a few references for also another type of states that you have in these strongly coupled theories, which are glue balls. So there's also been some work on 3-2 glue balls. So I'll give you a few references. The first is actually that original paper for cannibals by Carlson, Hall, and Machakek. So this is that paper in 1992. There's a nice paper by Soni and Zhang, which is from 2016. And there's also a nice paper from Forstel et al. From 2017, just as examples of how one can think of the glue ball states in these theories, and also there be using 3-2 interactions. Okay, and one more reference that I'll give before we move one step further is, so I gave you over here one reference, which includes using a kinetically mixed dark photon into the theory. And we spoke about that for SIMPs, especially, we have to have not just the 3-2 process, but we have to be able to mediate interactions with the standard model. We have to be able to shed heat, to dump entropy. And there are several portals that have been worked out in this context in the literature. One is the kinetically mixed hidden photon. Another one is the axion portal. So there's a paper by, together with Eric Kuflick and others, which is 1806.100139, which has the axion portal in it. And I know somebody in the discussion session the other day had asked about these portals. So some of the portals have been worked out, and I think there's still interesting work to be done to work out others as well. Okay, any questions on this sort of model building side before we talk about how these theories are also very predictive? Okay. So now that we've constructed generic classes of dark sectors that give us very interesting different realizations of different processes, the reason that I think it's not just exciting that these ideas are very generic. I think especially as phenomenologists, it's also very exciting that these ideas are predictive. So let me explain what I mean by that, okay? So let's look at this class of theories we've been talking about. So let's look at these QCD-like theories. And let's do times dark electromagnetism. Okay, this is just an example that we can work through, by no means the only example. Okay, so I'm going to add on to my story a photon, which is mixing through kinetic mixing into our dark photon. Okay, so this is our dark photon. And maybe I'll just note this paper that I referenced that includes the dark photon. It also shows how to actually embed how you naturally, within your global symmetry in these theories, how you can naturally embed the dark photon. So it's not like you're adding something new, it's completely within the symmetry structure of the theory already. Okay, so it's not something additional you have to tack on. But for simplicity now, let's just imagine the situation where I have this QCD-like theory, and I also have my dark photon, which is natural to have in this context. And so here's an example of what this sort of parameter space looks like, okay? So now let me fix my gauge group and let me fix my dark matter mass, and I wanna understand what happens from the dark photon side. Okay, so I'm gonna draw this now at fixed gauge group and fixed dark matter. Okay, so fixed dark matter mass. And so as a function, if I look at epsilon as a function of the mass of this dark photon, then there's a whole bunch of different, I can compute all sorts of different processes that happen, okay? And so here's a set of curves. So one curve I'm going to draw down here is a curve that talks about the thermalization. So this is the curve of, let's take this color, this is the curve of thermalization, okay? Where the elastic scattering between my dark matter and my like my dark pions and standard model particles happens. Okay, so this is one type of curve that I'm going to have that I can compute, and I'm also going to have a curve that looks something like this, which is going to be the curve where my dark pions are annihilating to two standard model particles. And so just kind of thinking of what this means. So so this curve over here, the top curve that I've just drawn, this is really the curve where, you know, if these 2 to 2 annihilations are if I'm along this curve, then my relic abundance is just set by 2 to 2 annihilations, and I have a WIMP-like particle. If I'm along this bottom curve over here and I have thermalization, this is, you know, this is the curve of where elder dark matter happens, okay, along this curve. If I'm beneath this curve in this region over here, then I'm not thermalized with the standard model. And if I'm in this regime between this top curve and this bottom one, this is the regime where where I'm thermalized, but I haven't been overtaken by 2 to 2 annihilation. So this is the SIMP window. And if I look down here, and this curve kind of goes down at twice the dark matter mass. If I look at what's happening to the left of this curve over here, then this is a region where semi-annihilations, so let me write that here, where semi-annihilations contribute. Okay, so in this very, very simple, simple theory that I've already written down, you see how different regions of the parameter space give me realizations of different mechanisms. Okay, so I get all the different phases of different dark matter processes that that could be happening. And so this sort of spans what is the parameter space, and this parameter space is already partially constrained. So we do have constraints on this parameter space. Constraints on the parameter space do exist, and these come from a whole variety of different experiments. Okay, so we have, if we're sort of listing what kinds of experiments, we have high energy and low energy experiments, that low energy colliders that are already that are placing limits. And so roughly speaking, let me think if I'll draw this first. Okay, I'm going to draw the types of constraints in a moment, but we have a bunch of different constraints on this parameter space, and we also have potential future probes of the parameter space. Okay, so that's sort of the most fabulous situation to be in, right? Where on the one hand, I've already been able to constrain part of the parameter space, but on the other hand, we have future experiments that will be able to falsify or perhaps detect something in this parameter space. Okay, so they're going to be able to probe. So we also have many future probes on this parameter space, and they also come from a whole host of different frontiers of where experimental searches sit. So they come both from high and low energy colliders, such as, you know, so this could be the LHC or the ILC or L2, as well as others. We have also constraints and future projections from beam dump experiments and fixed target experiments. Just to give you a few names of these. So for instance, there's could be from Apex or from SHIP, as well as others, and also constraints or projections from direct detection. So these are going to be, we're going to be talking about direct detection in detail together tomorrow. But this is primarily happening from, for instance, electron recoil experiments. So there's an experiment called Sensei or Super CDMS, as well as others. Okay, and so just to give you sort of a sense of what this what this looks like. So let me take this picture that we have over here, and what I'm going to do now is remove the labels that we have. So I'm gonna redraw it over here. Okay, so let me just redraw that over here. Here's my epsilon versus MV, and you know we have this. So we said we have curves that look like this, right? That are sort of delineating which regions of parameter space have which type of dark matter. And so roughly speaking, existing constraints, and this is like a good ballpark, you know, when you're trying to think of a model and understand whether your theory is already excluded or what are sort of the ballpark of parameters that are okay or not okay. So kind of roughly, you can keep in mind that the constraints right now on epsilon, let's say they go something like, let's say like this, obviously not really drawn to scale, okay, but everything above this is excluded, and the ballpark of this is like 10 to the minus 3 or 10 to the minus 2. Okay, so epsilon, depending on where exactly we are in terms of the mass of the dark photon, so let's say at around 600 MeV, and this is happening at around, let's say 10 GeV, and I think that I've drawn all of this now for fixing the mass of the dark matter to be, let's say 300 MeV. Okay, this is just slicing the parameter space in one way to give you sort of a broad brush of sort of rule of thumb of what to sort of keep in mind, okay? So epsilon is roughly constrained to be already 10 to the minus 3 or 10 to the minus 2, depending on where exactly what the mass is. But we have many, many future probes on this parameter space. So, you know, there's going to be some stuff coming in from sort of from Bell 2. So there's going to be Bell 2. I'm not going to really draw all of these. Okay, so actually, let me leave this on. Okay, so I'm going to draw now colored curves, and these are all the reach. You know, how deep in parameter space different experiments could hope to go. So there's some stuff happening here from Bell 2, and a whole bunch of stuff happening here from ILC and from LHC, and I think SHIP is going to sort of be probing regions down here. So sort of the combination of all of these different types of experiments are really going to be able to probe significant regions of this parameter space. Oh, and I should also show, I think the electron recoil experiments are looking like that, depending on what size they intend to go to. So there really is a lot of hope in upcoming years for us to probe sort of deep into this parameter space. So current constraints, again, just this sort of rule of thumb. Roughly, if you're trying to think of what's the, you know, how large can my kinetic mixing go, current bounds are typically of order 10 to the minus 3 or 10 to the minus 2 over a broad range of dark photon mass. And as I've just shown over here, we have many future probes. And of course, this plot is not the accurate place where you should be going back when you're trying to figure out what exactly are your are the size of your constraints. And so I recommend one place that you can certainly look in actually is maybe the most recent one that I can point you to. You can look at our Indy dark matter paper that I gave you a reference for yesterday, and maybe in the break I'll pull out, actually there's another good reference that I could give for where if you want to look at sort of the current status of where all of these curves are really sitting. So I'll make sure to add in to this whiteboard the reference for that. Yeah, there's a question, Emanuele.
Thank you. Yeah, this plot is for fixed dark matter mass, right? Mm-hmm. And before you show that dark matter mass that accounts for the relic abundance is between 10 MeV and 1 GeV, sort of, right? Mm-hmm. So right. How does the picture change with this?
So
range.
Yeah, you can kind of think one useful way to think of how things are changing. You see this dip. Let me add here in orange. Okay, you see this, right? We have this this dip. Okay, so why is this dip happening? This dip is happening at twice the dark matter mass, and that's because if you look back at, sorry, I'm going to scroll for a moment. Okay, very, very early on. I apologize if this is making anyone dizzy. Okay, take a look at at this diagram, for instance. Okay, so this is basically when we're going on resonance. Okay, so that's where we're getting this dip. Okay, and roughly the way that you can kind of think of this is that when I'm changing the dark matter mass, let's roll back to over here. When I'm changing the dark matter mass, this dip is kind of shifting, and a lot of the features that are sort of the constraints and like where's the reach of SHIP going to reach, or where is the Bell 2 curve curving up, or the current constraints from Babar. These are all happening roughly at that twice the dark matter mass, and what it has to do is whether those fixed target experiments or beam dump experiments, whether or low energy collider experiments, whether what they're looking for is an invisible signal or a visible signal. Okay, and so very often, if you're talking about the dark photon mass compared to twice the dark matter mass, that's going to determine whether my branching fraction, into dark matter is allowed or not allowed. So once I can decay into the dark sector, in these types of theories, you're basically getting branching ratio of 1 into dark sector. So depending on, really just, you have to think of it that I'm shifting where, if I shift the dark matter mass, I'm shifting where is this 2MD, M dark matter shifting to, and that's very often just going to sort of shift how your bounds and your constraints are going to shift based on whether they're looking at invisible decays or visible decays, or whether, what are the final states. But there's, very often what happens in these, when you look, so it's absolutely true, it's very difficult to describe, in full a parameter space where, you have to sort of choose your axes and fix a few. So what you'll sometimes, like what I've just shown over here, it's pretty easy to understand what's going to change. Very often in these plots that you'll see in the literature of the epsilon, like the hidden photon plots, what you'll see is that, for instance, they fixed a ratio between the dark matter mass and the dark photon mass. So that's the other sort of version of how these plots, usually with like a ratio of 3, So these are the kind of things that are really important to look at when you're, to notice if you're pulling up a plot of a constraints and projections for hidden photons. You definitely want to see, what have I assumed? That's really important. What have I assumed about the dark matter mass compared to the dark photon mass? And depending on whether I'm keeping the ratio fixed or I'm just fixing one and varying the other, things might change a little bit. But those are sort of the way that people slice the parameter space. Okay. Yeah, I see Tim. I see a question.
Yeah, one quick question also on the dark photon. So, as I understood correctly, then we literally take a dark QCD. So actually the dark photon should be precisely massless. How can we generate a mass term if it's not gauge invariant?
Yeah, so let me make that clear. So when people talk about these hidden photons, dark U1s, what we don't mean is that it's literally, we don't mean that there's another massless degree of freedom. So it has a mass. It can either get its mass through that U1, that there's like a dark Higgs mechanism happening in that dark sector, or there's something that's called a Stuckelberg trick, which is just a way in which you like literally just think of the parameter as, as anything that you want. So the mass of the dark photon is actually a parameter that you're free to take to be as heavy as, in principle, from the theory perspective, as heavy as you want or as light as you want. It's not that it's directly linked to the mass of the actual photon. So it's all we mean is that there's a dark U1. Okay, and I can do whatever I want with that dark U1 because it's not constrained, it's not U1 electromagnetism where I absolutely can't touch its mass.
Okay, so we just have a mass generating mechanism, but we don't,
exactly.
At this stage, we don't really care about what it is.
Exactly,
okay.
Yeah.
Thanks.
Sure. Any other questions before we go on break? Okay, so let's reconvene on the hour. Is that okay? Okay, great. So hi, everyone. By the way, again, a reminder, anybody who's willing and able to turn on cameras, I'd appreciate it. So I'm not talking to only Francesco and Diego. Okay, so what we did together until now was we sort of concluded at this beautiful plot, which showed us how we have a lot of hopes and prospects for constraining, probing, maybe falsifying significant regions of dark photon parameter space. But what I want us to work on now together is the fact that we can actually go even further. Okay, so we can go even further. Okay, and what I mean by that is that we can actually have hopes not to just be probing something related to the dark photon parameter space, but actually be able to perform spectroscopy of the dark sector to measure the spectrum of the dark states in our dark sector in a very special way. So we can perform spectroscopy of the dark sector. Okay, so that's what we're gonna work out together. And let me just give you the reference for this. So this is a set of papers that I've done with Kuflik and Murayama. So one of them is a reference I've already given you, 1512.07917, and there's a second paper dedicated to this, 1706.05008. Okay. So again, in order to understand what I mean over here, let's draw an analogy from QCD, okay, which as you see is often something that's useful. So let's draw an analogy from QCD, okay? So in QCD, we know, measure, understand for the most part. We've measured a beautiful resonance structure, right? So how have we done this? How do we know the beautiful resonance structure of QCD? And the answer is that what we've done, and we still do, is we smash electrons and positrons on each other. And then, as we smash them on each other, that goes to stuff, okay? So we smash E plus E minus on each other, and that goes to stuff. Of course, this stuff then goes to these hadrons, which we measure, okay? So this is sort of the picture to keep in mind. We take electrons, positrons, and it's going to stuff, okay? And there's some square root of S, our center of mass energy. And as we scan, what is that center of mass energy that we're smashing things in? What we're doing is scanning the stuff. Okay, so by scanning, oops, if we scan square root S, we scan our stuff. Okay, and this is literally the way in which we've obtained a beautiful picture, which you're probably somewhat familiar with. I'll just draw it here. Beautiful picture we are all familiar with, which just shows you the resonance structure of QCD. So probably this isn't the first time that you've seen this, but just as a function of square root S in GeV units, we can look at what happens to cross sections in some units. Let's say millibarons. It's not important. And what we see from that is we have the rho, and then we have the omega, and then we have all of these sort of resonances coming up with different energies. Okay, so this is here's the rho, and here's the omega, and here's phi, and here's J psi, and psi 2s, and the upsilon, which I'm probably going to draw very awkwardly, and up here is the Z boson. Okay, so let's say this is like at 100 GeV, this is at 10 GeV, this is at 4, this is at 3, this is at 1, this is at 0.7. But this is literally the way in which we've discovered the resonance structure in QCD by scanning electrons, positrons, scanning the energy at which we're colliding, and just seeing what happens. Okay. Now you can ask yourself, how could I possibly see this spectrum? How could I have detected these particles? How could I see this if I was working, instead of with the ability to change my center of mass energy and scan it, what if I was looking at a fixed energy machine? Okay, a machine that just had one square root S. Okay, so you can ask yourself, how could we see this at a fixed energy machine? Does anyone have an idea? So I'll give you one. Let me look at this diagram, and maybe all I need to do is tack onto this diagram. Let me do a different color here. A photon. Okay. So if I look at monophoton events, okay, processes where I'm just looking at this monophoton, then by adding a photon, the energy of that photon is now a tracer for the system that it's recoiling against. Okay. So by adding a photon, and let me just draw this, so I'll write this down. What we do is we look at monophoton events, okay? So we add a photon, and by doing this, this photon is now a tracer for the system it recoils against. Okay, so let me draw this this image that I just drew here. I'm just going to sort of rotate the lines a little bit so it'll be a little clearer. So now I look at E plus and E minus at a fixed energy machine that are going into a photon and some stuff. And so what happens is that the energy of the photon is in 1-to-1 correlation with that. So that goes like square root of S over 2, 1 minus the invariant mass of that system over S, okay? And so because that energy of the photon is in 1-to-1 correspondence to the system that it's recoiling against, I don't have to see that stuff in order to be able to know what's going on, okay? So this stuff no longer has to be standard model stuff that I'm trying to see, but this stuff could also be dark stuff, okay? So this works, we can do this for dark stuff too. Okay, so that's really the idea. Okay, so imagine that what's happening over here is that now I'm going to this hidden photon, and my photon is going into dark states. And so in this way, by looking at monophoton events at fixed energy machines, we can actually trace out the resonance structure of the strongly coupled sector. So let me just give you an example. So for instance, so one machine that is starting to work, that's going to continue, is a low energy machine. It's called Bell 2. Okay, so this is sort of the like the next version of well, of Bell, but also of Babar, if you've heard of these experiments. And so this is operating square root of S is like 10 GeV. Okay, and so let me show you what I mean by this. Here is here's the plot of what you could sort of what you could expect. Okay, so let's look here at so down here I'll write this as photon energy, say in GeV units. Okay, and let's look at events per, I don't know, 100 MeV. Okay, just some way for me to count. And what you would see if there was some dark sector, you'd be able to see something that, you know, that as you were scanning in your energy, just look at your energy and you're going to start seeing sort of these all these bumps that are coming in from, you know, your first dark resonance, your second dark resonance, your third dark resonance, your fourth dark resonance, etc. Okay. And so this spectrum that I've drawn over here, just as an example, is one for actually for a SIMP-like dark sector with particular parameters. But what you see over here is that really within through this idea of using monophoton events, you could hope at low energy machines to actually be seeing the resonance structure of this perform spectroscopy of these dark sectors. And in this example, for instance, that I've drawn over here, this is something that you'd get, for instance, you also can get this if your dark photon is very light, but the dark photon could even be very heavy. Okay, so for instance, this plot I've drawn over here, where I haven't given you any numbers, but here, this peak is, let's say, happening at 4.5, and this one at 3.5, and this one at 2.6, etc. Okay. So this, for instance, could happen with a dark photon whose mass is above 10 GeV. Okay, this particular one is for 12 GeV, this plot that I've reproduced here. Okay, so it would be a situation in which you wouldn't yet be discovering your dark photon, but you could actually be detecting that you have resonances, dark resonances that are of QCD-like nature. Okay, so this is what I mean by the ability to perform dark spectroscopy. Are there any questions on this before we move to now talking about general constraints?
A quick one.
Okay.
I would expect a huge background for this kind of processes. How can one disentangle the two?
Yeah, so it's actually not very large. So like the standard model background, I can draw that. So let's say you wanted to worry about like, let's say, so the only thing that would be invisible in this context in the standard model would be neutrinos. So if you want to look at that, it's actually significantly lower. Okay, so this is something that you could hope to do with, so this is, for instance, assuming like a 1 energy resolution, assuming you have 50 inverse autobarons of data. The only thing that's like super crucial here that you absolutely won't be able to do without is that you have to have a monophoton trigger. If you are not tagging your monophoton events, you're obviously not going to be seeing this. And this is something that Bell 2 has been working very hard on managing to get a monophoton trigger. Okay. Okay, great. So we're now going to move. We've now sort of concluded our dark sector discussion. We've seen how these mechanisms that we discussed together throughout our lectures are generic in theory land, and we've also seen how we have really hopes to probe them, these sort of QCD-like dark sectors in experiments, constraints, and interesting methods for detecting them. And what I'd like us to do for the remaining time together today is talk about sort of general constraints that you should sort of keep in mind when you write down a mechanism or a model and you're working through the details for your case. Okay, so just sort of a broad brush of types of general constraints. These are the constraints to sort of keep in mind when you write down a new mechanism or a new model and you're working through. So you want to work through these particular ones and all the others we've discussed, but some others that we haven't, work through the details for your case. Okay. So the first one is going to be sort of the category of a minimal mass bound. Okay. And there are a few different types of constraints that fall into this understanding what's the minimal mass. So the first one that I'll mention is what we call fuzzy dark matter bound. Okay. So this is something that I actually mentioned already in our first lecture together, where I sort of drew those 80 orders of magnitude of where of where the mass of dark matter could be, and sort of the lower end of that mass spectrum was being set by this fuzzy dark matter bound, which says that my de Broglie wavelength of my dark matter should be able to fit inside what we've observed. And so the real bound is coming from the smallest system. So the de Broglie wavelength should be smaller than the size of dwarf galaxies. Okay, so if I have, I have some galaxy over here, it's going to have some mass and some radius, and I better make sure that my dark matter can fit. Okay, and so this is the type of limit that tells you that the mass of the dark matter should be larger than around 10 to the minus 22 GeV. Maybe some discussion these days about is it moving to 10 to the minus 21. And this is a bound, though I'm also gonna try to sort of give you pointers to when you think of these bounds, it's a good rule of thumb, but also ways in which you can evade them. So this bound holds when your dark matter is a boson. It also holds if your dark matter is a fermion. So regardless of the bosonic or fermionic nature of your particle, but it does not hold if you have a subcomponent of dark matter that's less than 10%. Okay, so this is a way in which you can evade this, but if it's a larger component than that, boson or fermion, it has to be above this mass. So that's fuzzy dark matter bound. The second type of minimal bound on minimal mass bound comes from what's called phase space packing. Phase space packing. And this is something that holds for fermion dark matter. And it's sometimes called the Tremaine gun bound. Okay, and the idea is that Fermi degenerate pressure sets a minimal halo mass. Okay, there's a limit on how many fermions I can pack into a certain space. Fermions don't like, they're not the most friendly to each other. So there is a limit on how many fermions you can pack into a halo. And so the bound that you get from this is that M chi should be larger, dark matter mass should be larger than of order of keV. I'll just point out that there's more recent work. So more recently, this bound is maybe sitting at 0.1 keV. And I'll give you a nice reference about this. So if you want to read sort of about this, this more recent lowering of this bound is 1311.0282 for recent details. Okay, and this is actually the first way in which active neutrinos were excluded as dark matter candidates. Okay, so this is the first way. Let's take this color. This is the first way that we knew that dark matter is not active neutrinos. Okay, the ordinary neutrinos from our standard model. And in terms of when this bound of keV, so actually let me underline these also here. So this is the fuzzy dark matter limit, and this is our phase space packing limit. So I'll point out this bound of phase space packing, as I said, it holds for fermions. It does not apply to bosons. And it doesn't apply to, again, subcomponents of dark matter that are less than 10%. So that's the phase space packing limit. Now there's another limit, which is called the warm dark matter limit. And this one I think actually often gets confused with phase space packing, and you'll understand in a moment why, but I want to just clarify these are distinct physical reasons for placing a limit. And here the idea is that if we have dark matter in the early universe, then free streaming washes out substructure, okay? So free streaming washes out structure. So, structure in the early universe forms from overdensities of dark matter. So, if I have here's some, in my early universe, I have some areas that have a lot of overdensities or that don't have a lot of overdensities. That's going to determine where so over here, there's going to be some structure that's going to develop, and over here, there's going to be some structure that's going to develop. And if I have a dark matter that free streams, it's over here, and whoop, it's free streaming, then it washes out structure of certain sizes. And so roughly, the way to think of this is that structure is suppressed on scales that are smaller than the free streaming scale, And so what this does is set a limit on the dark matter mass. So the dark matter mass should roughly be larger than a keV. And a good reference to read up more on this is Astro PH/0501562. Okay. And roughly speaking, this, so this in principle, this applies for many thermal relics, but it does not apply to bosons that are, if you have particles, different types of dark matter candidates, which we haven't discussed, where these particles are being sort of produced at rest. Okay, so it doesn't apply to bosons that are produced at rest. So this usually includes if people talk about axions or dark photon, dark matter. This is something that doesn't apply towards it. And I'll also add that it does not apply to subcomponents of dark matter that are less than 10%. Okay. But you see, the reason that I think people often get confused between the warm dark matter limit and the phase-space packing is because the numbers come out to be the same. But I want to stress these are different physical reasons for why a limit is set. Okay. So we've worked through so far three types of constraints on the minimal mass, and the next one in line, which is something that's already come up a lot during our time together, is constraints coming from N effective. Okay, so the idea here is that we have constraints on how many new relativistic degrees of freedom beyond the standard model are possible to exist in the early universe at different epochs. So constraints on new relativistic degrees of freedom beyond the standard model. These are constrained by, there are actually two times at which we care, at which we have constraints. So one is BBN, which is happening at photon temperatures of order MeV, maybe slightly less, and also the cosmic microwave background, when CMB is formed, when T photon is of order in EV. Okay, and so what we have from these constraints, we sort of by convention, we define number of degrees of freedom relative to neutrinos. Okay, so that's just our sort of the convention in the field. So convention is to count degrees of freedom relative to neutrinos. So that means that I'll call delta N effective is the energy density of something sitting in your dark sector. Okay, any additional degrees of freedom normalized by the energy density in neutrinos. So this is 4/7 G star number of degrees of freedom in your dark sector over what's the temperature of your dark sector divided by the temperature of the neutrinos to the 4th power. Okay, so this is how I can define deviations from new relativistic degrees of freedom compared to what we already have for neutrinos, and the current limits or the bounds. So from BBN, what we have is that delta N effective should be smaller than 0.4. And this is something that comes from, there's a nice paper here by Fields, 1912.01132. And similarly, from CMB, our current bounds are saying that delta N effective should be smaller than 0.6. And this number is coming from the Planck collaboration, so 1807.062009. So this is from Planck. And this one is by Fields et al. So these are the size of constraints that we have right now for currently for additional number of degrees of freedom. I just want to point out that CMB stage 4, so new experiments that are planning to run, hope to constrain, maybe I'll change color for this, so CMB stage 4 intend to claim that they can get delta N effective to be actually an order of magnitude smaller, so around 0.05. Okay, so this is an order 10 improvement. Okay, so this is what we hope to be able to achieve in the future. And you know, so one thing that we can already take just from these numbers already is that you see that if I have a dark sector that has particles, that has a part that has a mass that's beneath the MEV scale, then just by looking at this equation for delta N effective combined with our current bounds, this tells us that the temperature of the dark sector has to be beneath the temperature of the photons. And so that means that that our sectors have to be kinetically decoupled at roughly MEV energy scales. Okay, so if we have a dark sector, well, let me put it this way. Okay, yeah, so if we have a dark sector with, you know, masses that are beneath an MEV, it must have its temperature be beneath that of the photons. And so it must be, said another way, it has to be kinetically decoupled at roughly MEV. Must be kinetically decoupled at sort of the MEV scale, okay? Or said another way, if it is kinetically coupled, then the masses should be above an MEV. Okay, so this is the other version of this to keep in mind. If it is kinetically coupled at MEV temperatures, then the masses should be above an MEV from this N effective bound. Okay. And so this is going back to a question that I think we had yesterday. This is one of the reasons why, for instance, in SIMPs, where we say we have to have this kinetic equilibrium, this is going to set the lower limit of the mass to be at the MEV, roughly at the MEV scale. Okay, so this, for instance, sets the SIMP bound, and also for others. So this is more general, of course, than SIMP, but this is sort of what you should keep in mind is that it's difficult if I have kinetic equilibration. I have to be very cautious about being coupled at the MEV scale. If I am, the masses should be above an MEV in general. Okay, and if you want to hear many more details about specifically all of these types of constraints, but specifically also about ineffective, there's a really nice set of lectures that you can watch that Josh Ruderman gave at a school that we organized here at Hebrew University just before the pandemic broke out. And it's available online. So I'll just point you to one particular one. That's the Josh Ruderman gave lectures at the Israel Institute for Advanced Studies Winter School. This is how you'll Google it and find it, 2019. And this is in lecture 4 of that series, okay? Okay, so we've discussed a little bit bounds on minimal mass. We've talked now about constraints from N effective. And the next type of bounds that I want us to discuss together are constraints that come from self-scatterings. Okay, so let's now talk about self-scattering. Okay, so we mentioned this actually at the first lesson when we were sort of going through the laundry list of dark matter properties that we know. And one of the things that we said is that, okay, we don't want dark matter to too strongly interact with itself because these dynamics distort, these types of interactions can distort the dynamics, in dark matter halos, okay? And so if we have, here's what I mean by self-scattering, okay? It's these scatterings where chi's scatter off of themselves and sort of redistribute their energy, redistribute how they sort of bump into each other and change some stuff. And the current limits in this context tell us that the self-scattering cross-section divided by the dark matter mass, this is how it's typically given, these should roughly be smaller than around the centimeter squared per gram. Okay, and this is a type of ballpark number coming from, this comes from all sorts of systems, but let's say this comes from the bullet cluster and from halo shapes. And I'll just say this number 1, there's some, this is going to be important, this number 1 over here, really there's kind of a range, let's say varies between 0.1 to 10. Okay, this number 1 over here. And really there's some dependence of velocity of the system. And so what exactly is that number? And so this is a type of constraint that we have on theories. But I'll just point out that there are also some interesting puzzles in structure formation that are really sort of long-standing puzzles in this context, which you might have heard about. And I call them puzzles. It's unclear if they are problems or are not. It really depends a lot on who you speak with. I tend to think of them as puzzles, where I'll explain in a moment. So one is called core versus cusp, and the other one is called too big to fail. Okay. So too big, so let's start maybe with core versus cusp. So core versus cusp is basically the statement that if I had dark matter that didn't have any self-collisions, then this would predict dark matter densities that are very cuspy towards the center. Okay, so they should sort of be shooting up, whereas observationally we see them to be flatter. Okay, so that means that what we would predict for cold collisionless dark matter would be something that, if I'm looking at what's the density as a function of the radius in some system, then, I don't know what it would look like there, but it should kind of go very cuspy, whereas observationally, we're seeing that there's a core, so there's this mismatch. And too big to fail is just a statement that if there's a mismatch between the Milky Way's brightest stars and its brightest satellites, okay, and its biggest satellites. So this one is a mismatch between Milky Way's brightest stars and its biggest satellites. Okay. Now, it's very possible that these issues are actually addressed by unaccounted for astrophysics. So, to be able to say whether something is missing or isn't, what is the prediction? These are something that involve a lot of very big simulations. And so it's very possible that these issues are completely addressed by astrophysics. So it can be addressed by astrophysics. And sort of the big thing in this context is that there are some unaccounted for baryonic effects. Okay, so maybe if people properly include baryonic effect into this story, these issues are resolved. And we're not astrophysicists. I'm not an astrophysicist. What I just want to point out in this context is that what these puzzles tell us is that if you have dark matter that has self-interactions of a particular size, there's room in the theory to accommodate that. Okay, so this might be, let's put it this way, that also if you do have self-interactions, so if you have a theory that predicts self-interactions of order exactly this limit of a centimeter squared per gram, that's something that could help and assist in solving these puzzles. So these puzzles, which are long-standing puzzles in structure formation, can be assisted by these strong scale types of interactions. And I say strong scale because this number of a centimeter squared per gram is roughly 100 barns per MeV. Okay, so this is exactly the strength of the strong scale interactions. Strong scale interactions. Okay, and if you want to read a nice review about this from the particle physics perspective, then I recommend this review by Sean Tulin and Haibo Yu, who've worked a lot on this topic. It's 1705-02-358 for a really nice sort of review of the subject. Okay, so the reason that I'm saying all of this is so you could keep in mind there's a bound from self-interactions, but also room for getting a contribution that's of order the bound. And in particular, if we think about the mechanisms that we've worked, the mechanisms and the models that we've worked together with, when we talked about SIMPs, we were talking about strongly interacting massive particles, which indeed had strong self-interactions. The ones that we had discussed are strong 3-to-2 interactions. But in general, in SIMPs, so I just want to sort of point out and show you like what this means in the context of SIMPs. So in SIMPs, you kind of expect in any theory, or in most theories that would have strong 3-to-2 interactions, to also have unsuppressed 2-to-2 interactions, right? That's sort of the natural expectations. If I have strong 3-to-2, it'll be surprising to end up with suppressed 2-to-2. So we kind of expect that strong 3-to-2 will also generically lead generically have, sorry, let me write this differently. Will also generically have strong 2-to-2 self-scatterings. Okay. And so, for instance, in the context of that, remember we wrote down our pion theories, these QCD-like theories. And so, again, just an example in this context. So in those theories that we've written down, if I look at all the different terms in the Lagrangian, not just zooming in on those 5-point interactions, then I'm going to get terms that, there are all sorts of terms, and I'm going to drop sort of the coefficients, but I'm going to get terms that go like pi to the 4th directly. And also I'm going to have terms that have, pi, basically like pi, d pi, pi. So I'm going to have different types of 4-point interactions in my Lagrangian. And I can go ahead and compute, given this Lagrangian, what does my self-scattering cross-section look like? And it's again going to be a function of my parameters. It's going to be m pi squared over 32 pi squared f pi to the 4th times some combinatorial factor a squared over n pi squared. Okay, so this is a combinatorial factor over here. This part is combinatorics. Okay, and I can go ahead and understand in the context of the parameter space that we've drawn before, what does the constraint on self-scattering tell me on this theory? Okay, so let's just draw that over here. So, so here is, remember we had this m pi over f pi as a function of the pion mass, right? And we have this solution to the Boltzmann curve, which I drew here, which told us that, so I had a limit over here. Sorry, let me just write that down. So we had some limit of m pi over f pi shouldn't be too large, right? From just staying in the perturbative regime of the theory. And that kind of sets an upper limit on the mass of the dark matter, right? And what I can do is along that solution to the Boltzmann equation, which is dictating for every m pi, what's the value of m pi over f pi, I can plug that into my self-scattering cross-section and draw what is the scattering cross-section that I get. And here's what I'll get. I'll get something that looks like this. Okay, so this is what I'm drawing here is what is this self-scattering over m. Okay, it's some curve, and it has to be beneath some value, right? It has to be beneath a centimeter squared per gram. So it's going to be beneath, some value, which is this 1 centimeter squared per gram. Okay, and so what that means is that now my self-scattering is actually dictating a lower value to my mass. Okay, and so combined, what I've ended up with over here is a very particular, really well-designated variable range for the dark matter masses. Okay, and so this is what you find from this is that really your mass of the pions in this story has to be of order a few hundreds of MeV. Okay, and so you're really sort of you're really pointed to a very particular mass range when you combine not just your relic density constraints but also your self-scattering constraints as well. Okay, so this is an example of how the self-scattering constraints really already feed into really restrictions on the parameter space. And the last constraint that we're going to discuss together today is going to be indirect detection. So this is another category of indirect detection. So when we say indirect detection, what we mean is, we have all these interactions in principle of, let me change colors, interactions of dark matter particles. So here are examples of interactions that we've already looked at. So I could have dark matter that's annihilating the standard model particles. And when I look at it, if this is happening today, then we're going to be able to see, hopefully, some signature of these standard model particles. We could also have dark matter that's maybe decaying into standard model particles at a very slow pace, etc. Okay, so the idea with indirect detection is that we look to the sky and we hope to see via telescopes or satellites either the annihilation or the decay product of some dark matter interactions that are happening. Okay, so we look to the sky and hope to see, let's call it annihilation or decay product of dark matter interactions. And what are these products? You know, it could be anything. It could be photons, it could be electrons and positrons and muons, and you know, anything that you can think of. Okay. And so basically by looking at the flux of, you know, by considering what is the flux of these particles, well, we have limits of these types of interactions of gamma rays that we can see around us. And so we have this flux is going to set limits, and we have measurements over, I'll call it a broad range of energies, and just to sort of give you sort of a picture of what this looks like. So and I'll give you the reference for you can see this in more detail in a moment. So if I just think of, you know, what is this flux as a function of, let's say, photon energy, and let's actually in MeV units, let's do this in MeV units, then there are all sorts of different experiments that have been measuring this flux in different energy regimes. And so, you know, there's some experiments that are measuring over here in this energy regime, and then there's going to be some other experiments measuring over here, and something going on over here. You know, and another experiment taking over here. So, so sort of this high end of the spectrum is really where the Fermi, and also there's something called egret sits, and many others that that are sort of spread out over these energy ranges. Let me just add some axes over here. So this high end is, let's say, over to 10 GeV going down to 10 MeV. Over here, this is something that sort of slides over at the MeV range, and you can go down here even to 50 kV. And kV is really sort of where, at least the plot that I'm drawing right now sort of ends. And if you want to see more details about this in different models and how they would, just sort of examples of how you take either decay products or annihilation products of different particles and how you'll translate it into this sort of flux, there's a nice paper by Reuven Essek et al. From 2013 that does this. And so roughly speaking, you see that as a function of what is the energy of your products, et cetera, there's going to be, you know, some type of constraint that's roughly that, you know, that somewhat is dependent on the particulars. So this sets bounds on late time annihilations or decays of dark matter. And there's also, of course, constraints from energy injection into the CMB, and there's really nice lectures actually on this. I'll give you another reference here. There are really nice TASI notes by Tracy Slater. I think you can find this at 1710.05137. But sort of the ballpark that you get from all of this is you roughly find that for a decay, that the lifetime that you get for your particle should be, again, depending on the details, it's either between 10 to the 24 to 10 to the 28 seconds. It depends on, so this is going to depend on what is the mass of your dark matter and what are the final states that it decays into. But I think sort of a useful rule of thumb when you want to think, okay, I have my dark matter, how long do I have to make sure it lives for? It's not just the age of the universe, but it's actually stronger than that. So sort of a good ballpark is, you know, a good ballpark for sort of the rule of thumb ballpark is going to be to sort of think of make sure that it lasts 10 to the 27 seconds. Okay, that's sort of a useful number for you to play around with. Okay, so that's all I wanted to say about indirect detection. And the last, but certainly not least, category of constraints, which we are going to be delving in super detail tomorrow, is direct detection. And that's really going to be the focus of our entire last lesson together tomorrow. So that's all I wanted to share today. Are there any questions?
Okay, so we will, oh, sorry, there is a question. Go ahead.
I'm sorry. Can you explain more about from the too big to fail problem?
Say that again.
Can you explain more about too big to fail problem?
Too big to fail?
Yeah, I want to know more
okay.
details.
Yeah, so first I want, Yeah, I just want to be very cautious with the language. I don't call it a problem. There might be other people who will call it a problem. I'm going to call it a puzzle. And the idea is that if I look at the biggest satellites in the Milky Way, they're just too big to be hosted by the brightest stars that we observe. Okay, so it could be that we're just, for instance, maybe we're not observing yet. You know, maybe there's as our machines get better and better, we're going to be able to observe things that are fainter and fainter. But from what we, you know, but that's the problem. The puzzle as is the fact that there's this mismatch between our biggest satellites versus they're too big to be hosted by the brightest stars that we've seen in the Milky Way. Okay, but I highly recommend reading this this review by Sean and Haibo, because it really has I think you'll find a lot of details there about both about the evolution in time of these puzzles. So there's a different version of this one. For instance, there are different versions of what you call this puzzle. The understandings have been evolving over time, but I think there are many astrophysicists who you'll ask, and they'll say, "Oh, well, if you include baryonic effects, some of this goes away. To what extent we understand this properly, I don't know." I think my takeaway from this I try to be very cautious in this context, is you know, the combination of one. Okay, I have a ballpark of which is velocity dependent of what is the size of my constraint, but understanding that if I have a contribution, the dark matter contributes. So me personally, I don't construct models in order to explain these puzzles, but if I have a model that gives me that as a side effect, then it's something that is potentially interesting. Okay, so that's, for instance, what happens for SIMPs. They have these unavoidable large contributions. They happen to be exactly in the ballpark to be addressing these puzzles. So I think that that's something that that carries some interest in it.
Okay, I've got it. I will read that.
Okay. Any further questions for today?